Hello, everybody. It is my pleasure to speak at DATE conference this year on the topic of digital twin for manufacturing systems. I'm Mohammad Al Farouk, an associate professor from the University of California, Irvine, and directing the Embedded and Cyber Physical Systems Lab. Several co-researchers are involved with me developing this idea. Besides Dr. Muthia Ran and Professor Karganekar, my graduate student Shiwan are also involved in this research. Before going to explain digital twin, let's discuss the new paradigm and revolution we are witnessing in the beginning of this 21st century. If we look onto the figure, in the left of the figure, we see the first industrial revolution. Enabling technology for the first industrial revolution during the end of 18th century was steam engine. In the beginning of 20th century, the second industrial revolution happened. Enabling technology for the second industrial revolution was electricity. During the 70s, the third industrial revolution was possible due to innovation of electronics and information technology, which expedited further the automation. The question is, why are we talking about Industry 4.0 today? What has enabled this revolution? In 2006 in USA, especially in National Science Foundation, the program Cyber Physical System was initiated. Cyber physical systems were termed as integration of computation and physical process. Now, if you see the figure in the left, you will see that cyber physical systems brought multiple disciplines, including control, autonomy, data analytics, IoT, privacy under the same umbrella. And this flower diagram shows that all these research disciplines can impact under this umbrella several applications from automotive to aeronautics to agriculture and definitely manufacturing systems. We quickly realized the immense advantage of connecting these cyber physical systems on the internet, what we call Internet of Things. Although internet was not optimized for IoT, now we see a lot of R&D focus to make this suitable for cyber physical systems. To make things clear, in the context of this presentation, Industry 4.0 is mostly along this new paradigm of cyber physical systems in the manufacturing domain. Let's talk about the key stages for realizing the vision of Industry 4.0. The figure has been inspired by the description of Arctic Industry Maturity Index explained by FIR Arvetia Akhener. At the bottom of this pyramid, we see the digitization part, and by which I mean the computerization and connectivity. And then comes the visibility. And visibility is a key for assessing the manufacturing floor changes and operating conditions. This will impact every decision in the production pipeline. After that comes the transparency and predictive maintenance, which are essential for understanding how to respond and directly affect the performance under changing circumstances. Finally, at the top stage is the adaptability that will enable the system to respond to a changing situation by itself instead of human in the loop making the decision. Now, in each of these stages, digital twin can play a huge role for in Industry 4.0. Now, what is industry digital twin? Digital twin was first coined in 2002 in NASA for the flying objects that they are building, and they define it as that it will integrate multi-physics, multi-scale, and probabilistic simulation of the as-built vehicle or the system that uses the best available physical models, sensor updates, fleet history, or maintenance history to mirror the life of its corresponding flying twin. And then this concept basically find its attention into several disciplines, mostly into manufacturing. And over the last several years, we find applications and uses of it more and more. One of the recent definition of about digital twin is that a digital twin has a digital and a virtual part and a physical part and a connection between digital twin. I'm going to give you an example in the context of cyber physical production system. In this picture, you see that the major building blocks of the digital twin are data, models, and algorithms. And it has so many capabilities like visibility, transparency, predictive maintenance, and availability. And these various use cases can be built using these constraints and the capabilities that we said, like from design to autonomy and optimization. This building of digital twin is possible over the last several decades. There has been several technology innovations, or what we call enabling technologies, like artificial intelligence, smart sensors. Now, if you want to think about the production system, in the production system, there are typically four parts of the what we call physical twin. like the component twin, the product twin, the process twin, and the system twin. And between this digital twin and the physical twin, there will be communication, like real-time and operational data will be collected from the physical twin, and also feedback will be given in real time to the physical twin from the digital twin. So you see that two-way communication can be established between these two twins. As I said, these are the classic view that digital twin and physical twin, they are connected, and learning already is involved into this today's standard view of the digital twin. In the context of this presentation, we proposed a new type of digital twin, what we call cognitive digital twin. And this cognitive capabilities or cognition has been inspired by the definition by Ulrich Neisser into the area of cognitive psychology. And he defined cognition as refers to all processes by which the sensory input is transformed, reduced, elaborated, stored, and recovered. Now, in this context, that if we take this definition and try to incorporate within the digital twin, we can get a couple of characteristics like learning, perception, attention, memory, and problem-solving capability. We need to incorporate in the digital twin. Now, the question is, what is learning? So learning is the process of transforming experience of the physical twin into reusable knowledge for a new experience. Then comes the perception. The perception is the process of forming useful representation of data related to the physical twin and its physical environment for further processing. Then comes the attention. Attention is we can define that a process needs to be selectively focused on some task or goals or some certain sensory information. And another most important thing is that we need memory. Memory allows the algorithms that we are building to remember the context, and additionally allow the digital twin to leverage the past knowledge. And then we need, as I said, the problem solving and reasoning capability. And you know that these are the cornerstone of human intelligence, am I right? So we can define them in the context of cognitive digital twin as that we can draw conclusions which are consistent with a starting point. So this is this definition. Now, if we take for the context of the proposed cognitive digital twin, and if we want to implement into manufacturing context, then you will see that we can implement a couple of operations into digital twin. So one of the first operation that I'm going to present here is called search operation. Like, what we mean by that, that we want to identify the appropriate digital twin model of a manufacturing system by searching over the internet, or just like a Google search engine today you see. And if we want to accomplish such a function or operation, then we need multiple of cognitive capabilities like attention, memory, perception, and problem solving to be incorporated into this operation. The second operation that I see is envision is the scale operation, which can be like passing relevant information gained during the life cycle of the digital twin of a manufacturing system to a new digital twin. And this, to achieve such an operation, you will need problem solving and reasoning capability. And one digital twin may be applicable in another digital twin model. For example, the digital twin model for a manufacturing system to predict the built 3D object surface quality may be applicable in predicting the geometric variation. Finally, the third operation that we envision is the share operation, basically, which means sharing knowledge across non-overlapping domains. It might be very interesting and useful to know how knowledge transfer can be performed across multiple domains, such as manufacturing system with different technology. For example, a digital twin model developed to predict a failure may be utilized to model digital twins responsible for a quality maintenance. Now, there are several research challenges. In fact, one of the first research challenges that we have to think about, how do we take these abstract concepts and mathematically represent them? Am I right? And then to enable these things, second research challenge is to enable them into cognitive digital twin, we need high performance computing and much more accurate numerical simulation tools. And the operations that I presented, search, share, and scale, how to implement these operations basically, and what are the ways that we'll be implementing these things. These are hard questions to solve going forward. So let's summarize my short presentation now here. I presented a conceptual framework of cognitive digital twin, and it will be used in all stages of the manufacturing systems. And then I presented three operations that we can achieve basically in a cognitive digital twin. And for doing that, we'll need a multidisciplinary research to accomplish such a goal. With that, I will conclude my talk and thank you